So today we're going to just go over curve sketching again and some of the different things to look for, things that can help us when we're trying to sketch a curve. So the first thing to do, and I guess I'm talking about functions which are more polynomial type ones. And so you'd rewrite the function as one complete fraction. Y-intercepts, always very easy to find. You just substitute in x equals 0. And similarly, x-intercepts, they're easy to find. When you've got a fraction, it's got to be the top of the fraction that equals 0. So you just solve the numerator is equal to 0. Then you go and do a polynomial division, and your function will now look something like this. Instead of being a polynomial over a divisor, you get the quotient plus the remainder over the divisor. Now, when it's in that format, that tells you a lot of information. So the bottom of the fraction, we know the bottom of the fraction can't equal 0. So if we solve that equals 0, that'll tell us where the vertical asymptotes are. The quotient, that will always tell us where the horizontal or oblique asymptote is. It just depends what that quotient is. Obviously, if it's just a number, then we've got a horizontal asymptote. If it's some function, I don't know, let's say it's 5x, then 5x would be the asymptote. And then the top of the fraction, when it's in this form, so the remainder, if it's possible for that to equal 0, that will tell you if the curve actually cuts that oblique or horizontal asymptote. So lastly then, you look for symmetry. You might not always notice it, but if you do notice it, then it's going to help you with your sketch. Because if you spot that it's an odd function, then you know it's got rotational symmetry. If you spot it's an even function, then you know it's got reflectional symmetry in the y-axis. And the other one to keep an eye out for, and this one's not always easy to spot, is that symmetry in y equals x. And that's the ones where it's its own inverse. So if you swap the y's and the x's round, you still have the same function. As I say, not as easy to spot, but if you do spot it, then you know, okay, it's symmetric along that diagonal line. So let's talk a bit about asymptotes. So vertical asymptotes, they're the ones where we have an exclusion in the domain. So it's not possible to substitute in an x value. So for that reason, the curve can never cut it. So they never go across a vertical asymptote. The next type were those horizontal or oblique ones, but horizontal ones, more importantly, that's when a function, what we call, converges to a specific value, or the limit as x approaches infinity or x approaches minus infinity is some constant number. We get a curve that out at infinity is approaching those values. But horizontal ones tell you what happens out at infinity. So for that reason, it is possible for a curve to cut it somewhere else. And that's why we have it in that fraction. We look at the top of the fraction, and is it possible for the remainder to equal to 0? There are 3 limits that can be very useful, and it's going to affect the horizontal asymptote. So 3 things to keep an eye out for. The first one is that special limit we know, and it comes from the hyperbola because we know what the hyperbola does. So if you spot in yours, you've got 1 over x, or you can create 1 over x, then you know then that will approach 0 when you substitute in infinity or minus infinity. The other one's an exponential. So e to the power of minus x. So that's our exponential, or I like to call it the backwards exponential. So it starts off really big and then comes down and goes asymptotic to the x-axis. So we know when we've got e to the power of minus x, as x approaches infinity, the e to the minus x must be approaching 0. The third limit is the reverse of that. So if we have our regular exponential, which starts off asymptotic to the x-axis and then gets bigger and bigger, now it's when x approaches negative infinity that will become 0. So they can be useful to keep in mind. So for example, and we've seen ones like this, so x squared plus x on 1 minus x squared, because remember, you can't substitute infinity into a function. I mean, infinity is not actually a number as such. It's more an idea, I suppose, of being the biggest thing we could possibly have. So you can't substitute it in. We always investigate what happens as x is approaching that value? Well, I can't sub it in, so I've got to use this idea that the limit of 1 on x is equal to 0. So I've got to get 1 on x into that fraction. So what I do is I divide everything by x squared. That way, when that simplifies down, the only place I find x is in the bottom of the fraction. And that's fine, because I know that the limit, when the pronumeral is in the bottom of the fraction, if it's approaching infinity, that will go towards 0. So for my one here, I'll end up with 1 plus 0 on 0 minus 1, which is negative 1. Well, the quick way of doing that, you might remember, is just to look at the coefficients of the biggest power. And so the biggest power there is x squared. And so the biggest power, its coefficients, on the top we've got 1, on the bottom we've got minus 1, minus 1. So we've seen ones like that. What about something like this? As x approaches infinity, of e to the power of x plus e to the power of minus x over 2 e to the power of x. So we're going towards infinity. So the limit I want to use is the e to the minus x. Problem is, they're not all e to the minus x. Some are e to the power of positive x. So I want to make all of those exponential powers negative. How could I do that? Well, what I'll do is I'll multiply everything by e to the minus x. Why did I choose e to the minus x? Well, because when I multiply e to the power of x with e to the power of minus x, the exponential now disappears. So I want to make the positive powers there disappear. So I multiply everything by e to the power of minus x, and I end up with 1 plus e to the power of minus 2x over 2. But now I can do the limit, because I know that e to the power of minus 2x, that bit is going to approach 0. So I'm just left with a half. I can do the same sort of thing if I'm looking at negative infinity, so it's the same function, but now I'm interested in what happens at negative infinity. Well, in this case, I want to get rid of the negative power. So e to the power of minus x, how will I get rid of that? Well, I'll multiply it by e to the power of x. So we'll multiply everything by e to the power of x this time. And so I'll get e to the power of 2x plus 1 on 2e to the power of 2x. Well, now because I'm going towards minus infinity, those exponentials will go towards 0, and I'm left with 1 on 0, which is undefined. We usually think of it as, okay, that's heading towards infinity. I mean, 1 on 0 is not actually equal to infinity, but it's sort of how we think about it. It's like the tan function. When we were looking at boundary values for tan functions, you might remember that we ended up with 1 on 0, so we knew, oh, that's going towards infinity. So there's some ideas that can help with horizontal asymptotes. Let's have a look at this graph. Y equals x cubed minus 9x over x squared minus 4. They want us to find the asymptotes, points where the graph meets the axis, all those sorts of things. So let's start off. Y-intercept, always easy to find. Sub in x equals 0, and I get 0, don't I? Of course. When x is 0, that whole thing's going to be equal to 0. Then x-intercepts, sub in y equals 0, and I need to solve that, and I'm getting x equals 0 and x equals plus or minus 3. So I could plot that in. So I've ended up with a 3 x-intercepts, the 1 y-intercept. The y-intercept turns out to be the same as the x-intercept because it happens to be 0, 0. All right, let's do the polynomial division then and see what we can draw out from that. And we end up with x minus 5x on x squared minus 4. All right. So all the different things we can tell from that. Vertical asymptotes. Bottom of the fraction can't equal 0. So in this case, x can't equal plus or minus 2. We know we have vertical asymptotes at plus or minus 2. So let's dot those in. Right. The oblique asymptote, with our one, that's going to be y equals x. Can the curve meet our asymptote? Well, that's where we look at the top of the fraction. Is it possible for 5x to equal 0? Well, yes, it is, when x equals 0. So our curve will actually cut that asymptote at x equals 0. So there's the oblique asymptote. We should have known it was going to cut anyway because we already knew 0, 0 was going to be a point. That's pretty much enough information to draw our curve. Because remember, we know that the curve's going to bend towards the asymptote. It must go through those points that I've plotted. So on the left-hand side, it must, I guess, start towards that vertical asymptote, come down and bends down towards y equals x. Similar thing is going to happen over on the right-hand side. What's going to happen in the middle? It could start up high, go through 0, 0, and then come down and go asymptotic to the other one, or it might be the other way around. How can I tell? I just got to substitute a number in, and then I know where it is. Oh, the other thing, I didn't spot it straight away, but that is an odd function. So that means we have got rotational symmetry as well. So that can help us when we're drawing our curve. That's what it actually looks like. So there you go. That's what I was saying about it bending towards the asymptotes, coming through those points, and we can see in the middle section what it's doing there as well. So that's a bit of a recap. A couple of new ideas there as well with those exponentials and what happens with the limits. So 3b and 3c, I've pulled some out.